Hello, I'm Steve Reyes, Product Manager for Anritsu Company. And today what we're showing is the new noise figure option for Vectorstar. It's the ability to analyze differential devices, so it's a differential noise figure measurement capability that we're providing now. What we are doing is taking the same basic technique of cold source measurements for noise figure in a single-ended version and applying that to the differential devices, but with some added capabilities to analyze and extract out the additional differential errors that you might find in a measurement. So what the typical situation is for a cold source method is to terminate the DUT and measure the noise power of the DUT. In order to do that, you must first characterize the system. So we do that by first measuring the DUT, getting an SNP file, and then storing that for later use. We then analyze the receiver path that the DUT is going to be connected into. In this case, since the power for the DUT could be quite low, we need to use a composite receiver which preamplifies the signal and filters out before going into the VNA receiver. So we need to calibrate the receiver first by injecting a source into that receiver and obtaining the calibrated measurements of the receivers. We then calibrate for noise power, and we do that by terminating the input of the receivers and then measuring the noise power. So once we've done those things, we're ready to make our measurements. We would go in and configure the noise figure measurement at that time. So in the terms of the differential noise figure option, we have some new capabilities that provide us with a choice of the types of techniques that we can use. So we have uncorrelated method, a correlated method, and then an output combiner, which is basically a balun approach. And so the uncorrelated method is the traditional way that people would have done this in the past by going in and making noise figure measurements, single-ended noise figure measurements on each of the paths in a differential device. The problem with that is if there's cross-correlation, correlated noise powers across the paths, then you're not going to properly identify all of the noise that's present in the DUT. So if, let's say that the device is well isolated and you have very good isolation between the two paths, that technique might work, fairly well. But as you get more into a differential pairs type of architecture, then you're going to be struggling with correlation and other noise issues. Another thing that people have been doing in the past is using a balun. And so by connecting the output of the balun, you end up with a single output, and you can now make your single-ended noise figure measurement. So that might reduce the number of connections and measurements that you need to do, but it doesn't take into account the correlated noise powers that we are still having to deal with. You can de-embed the balun through a standard SNP file, but that's usually just for magnitude and phase and the imbalance of the combiner, but it doesn't, again, take into account the correlated noise. So what we have introduced in Vectorstar is a new algorithm that measures and analyzes the correlated noise in the measurement system and then extracts that out in order to give you a corrected differential noise power. And so we have, again, provided three different methods, and the methods of the correlated approach or the output combiner both give you that corrected version of measuring, identifying, and extracting out correlated noise. So we provided the combiner approach, therefore, for people who have done measurements using baluns in the past and want to just use this new technique to improve on the corrections of that measurement in order to validate and to verify and to take forward in their accuracies, the measurement of differential noise. But really, the correlated method is going to be most likely the preferred technique, because you don't need the balun in that case. We're doing all of our corrections inside the receivers and doing that during our receiver calibrations. So since we're using two receivers at the same time and they are coherent, we're able to therefore in real time measure the correlated noise powers and take them out of the measurement once we've had our calibrations performed. So that's the approach again. With a correlated measurement technique, we take our differential device, run it through two composite receivers. It can be just one composite receiver, but for real-time, active real-time updates, you would want two, and then run those into our receivers, and from that we get our corrected measurements of differential noise figure, plus all the other parameters like noise powers, etc. And so this technique can be applied to both 3-port and 4-port devices, and it can give you all the information that you're looking for in terms of analyzing properly differential noise figure measurements. Thank you for your attention, and if you need any more information from us, please visit our website at www.anmitsu.com. Thank you.